Boxing Day, 2004. The world was shocked by one of the worst natural disasters of all time. Over 250,000 people died. The cause of this devastation was the most powerful kind of earthquake on the planet, called a megathrust. This event made us realize how poorly prepared we are to face these huge geological catastrophes. And scientists are now trying to work out where else is at risk. They have discovered that a megathrust as large as the Sumatra quake could hit North America. Everyone knows that America is going to be struck by a devastating earthquake. For years, the people of California have been waiting for the day when the San Andreas Fault unleashes the big one. But all the time, an even more powerful hazard has lain undiscovered. A giant megathrust earthquake, just like the one that hit Indonesia, threatens America's Pacific Northwest. A huge area from Northern California all the way to Canada is at risk, including major cities like Seattle and Vancouver.
It was a major earthquake.
We're just coordinating the emergency response that's going on.
The authorities have started to prepare for this catastrophe. Rehearsals like this one help to train the emergency services to deal with such an event. Children are now being taught lessons in survival that could mean the difference between life and death. The source of all this danger? Lying underwater off the Pacific Northwest coast is a huge gash in the Earth's crust, a subduction zone. The Earth's crust is made up of huge plates of rock that are constantly in motion. Where two of these giant plates meet head to head, one of them can get pushed down under the other. This is a subduction zone. It was a subduction zone off the coast of Sumatra that caused the Boxing Day earthquake. And worldwide, there are many other similar faults.
There are subduction zones all over the planet, but mainly they occur around the rim of the Pacific, the so-called Ring of Fire. And lots of big earthquakes occur there, most of the world's really destructive earthquakes.
Subduction zones cause earthquakes when the plate that's being pushed down gets stuck. As it pushes, the upper plate gets squeezed and distorted. Eventually, the strain becomes too much. The upper plate slips, creating a megathrust earthquake.
A megathrust earthquake happens when the subducting slab, which is diving under the overriding plate, is locked and causes the overriding plate to bulge upward. And then when that becomes unlocked, it slides suddenly, creating a huge earthquake. Worldwide, these are the biggest earthquakes. They range in magnitude up to 9.5.
Generally speaking, if you have two great masses of rock and you're scraping them one underneath the other, they're not going to move very easily. You're going to get a lot of friction there. And I liken it to sort of two cheese graters pushing past one another. Very, very difficult to get any smooth sort of movement there.
But as the 26th of December showed, megathrust earthquakes have another devastating consequence.
In the case of a megathrust earthquake, the overlying plate, which has been bent, pings back upwards into position. And it's that sort of pinging motion that transmits an enormous amount of energy to the seabed. That energy is then transmitted to the water above it, which oscillates up and down and then moves out as a series of huge ripples. And that essentially is what a tsunami is.
A tsunami is very different from a normal wave. In normal waves, only the water on the surface is moving. But a tsunami involves the movement of the whole water column. Millions of tons of water.
Normal wind-driven waves have very small wavelengths. That's from crest to crest. So there may be only a few tens of meters and then the wave has crashed and it's gone. Tsunami have wavelengths that can be hundreds of kilometers long. So when that initial wave comes in, the water behind it is pretty much at the same level. And that can keep coming for 5 or 10 minutes as a huge flood. And that's why they're so destructive. It's not a simple wave that you can hold your breath under and survive.
The combination of massive earthquakes and tsunamis makes subduction zones a deadly geological hazard. And so it should have been a cause for concern that the Cascadia subduction zone, a 600-mile-long fault, lies right off the Pacific Northwest coast. The strange thing was, Cascadia didn't seem to be a danger at all. For years, scientists had been monitoring seismic activity along the Cascadia subduction zone. They found that, unlike other subduction zones, it was virtually silent.
People saw that Cascadia had many of the features of a subduction zone. It had an oceanic trench, it had a line of volcanoes above the subduction zone. It simply didn't seem to have big earthquakes, and so they put it in a category of its own, the subduction zone that doesn't have big earthquakes.
And there was a simple explanation for why Cascadia wasn't creating earthquakes. If the plates were moving smoothly past each other, there would be no strain being built up, and no earthquakes. This theory was backed up by over 200 years of historical record. For as long as the Europeans have lived here, there's no record of any significant earthquakes from Cascadia. But in this region, there is another kind of history, a kind that isn't written down. For centuries before the Europeans arrived, this land was home to native peoples. Viola Reeby is a member of the Hoh Nation on the northern Washington coast. As a child, she was taught the legend of the Thunderbird.
The Thunderbird lives in the glacier at the headwaters of the Hoh River. When he comes out, the ground would start to shake, and he would even make the waters troubled.
Could this legend be describing a real event? A megathrust earthquake that occurred long ago. Most geologists had no time for such speculation, but one decided to take a closer look. Brian Atwater wondered whether the native legends might be a warning that the Pacific Northwest could be at risk from giant earthquakes. So he took to his canoe and started exploring the marshes and rivers of the Washington coast. He was hoping that the layers of mud here, laid down over centuries, might provide a clue to the events of the past. And buried in the marsh, he did find evidence of an unusual event.
We're on an ordinary coast, standing on a salt marsh like this one. Underneath, we find salt marsh deposits, salt marsh deposits, salt marsh deposits. just steadily on. But here, we have something completely different. We've got a spruce forest here, underneath the salt marsh. We can dig out here the bark of Sitka spruce.
These trees can only grow on dry land. Yet this layer of trees was covered with mud that must have been deposited by water. So the land here must once have been higher, and then, at some point, it dropped down, plunging the forest underwater.
At the time that the spruce forest dropped down, sand was laid down. It's the first thing that covers the peat is a little skin of sand. So that's the mystery. How did that happen?
Since there's no sand nearby, there must have been a sudden rush of seawater that carried the sand in with it. This was no gradual change in land level. It must have been a violent collapse.
The easiest explanation for that is that you had an earthquake that caused the land here to drop and also warped the seafloor. That warping of the seafloor set off a tsunami, and the tsunami then lays down the sand on the freshly down-dropped land surface.
Carbon dating of the buried trees showed that this event had occurred roughly 300 years ago, before Europeans had arrived. So the native legends might indeed be about a real event. But it would need more than just layers of mud to prove that there had been a devastating earthquake here. The next piece of evidence was to come from thousands of miles away. As the Indonesia earthquake has shown, megathrust earthquakes cause damage at astonishing distances because they create tsunamis. If such an earthquake really had occurred in Cascadia, it should have created a tsunami capable of traveling right across the Pacific to countries like Japan. Kenji Satake is a geologist who studies earthquakes and tsunamis. When Satake heard about Brian Atwater's theory, he realized Japan could hold the answer.
300 years ago is prehistoric time for Americans, but in Japan we have documents that would record the tsunami from Cascadia 300 years ago. So that's why we started looking for the records.
What Satake was looking for was a very special kind of tsunami. Most tsunamis in Japan are caused by nearby earthquakes, so they're accompanied by shaking of the ground. But a few tsunamis arrive without shaking, because the parent earthquake is far away. When there's no known earthquake that could have caused the wave, it's called an orphan tsunami. So Satake started hunting for records of an orphan tsunami that could have come from the Pacific Northwest. And in the coastal town of Miho, southwest of Tokyo, there's a document that describes just such a tsunami.
On this page describes the tsunami of January 28th, 1700. On that day, from morning, the tsunami arrived this town, like a high tide, and the receding wave was like a big river, and it continued like 7 times until the noon of the day.
The account told how the villagers took refuge in a shrine that still exists today. The author also recorded that this tsunami was unlike any that he had experienced before.
Writer noted that there was no earthquake, but the tsunami arrived, so he was surprised. And he said such a strange thing should be passed to the future generation.
Crucially, the same tsunami was recorded in 4 other accounts from different parts of Japan. So this couldn't be a local event. Satake thought this tsunami might indeed have come from a huge megathrust earthquake 5,000 miles away in Cascadia. But still there was no proof that the tsunami had come from North America. The carbon dating only showed that the Cascadia event had happened at roughly the same time as the orphan tsunami. The final piece of evidence would be found in a mysterious corner of the Pacific Northwest. A 100 miles southwest of Seattle, in a remote area of the Washington coast, is the Ghost Forest. These are trees that died hundreds of years ago, but remain standing to this day.
Sometime in the past, this would have been an intact red cedar forest. Large trees standing 100 feet or more in the air. And this landscape was filled with them. And then one day, something killed the trees here in place. And the mystery is, what killed them? You know, what could kill an entire forest along 60 miles of Washington coast, just like this?
Tree specialist David Yamaguchi has spent years trying to solve the mystery of what happened to the trees. He wanted to work out when they had died by looking at their tree rings.
Most people know that trees have annual rings. So depending on the climate from year to year, the tree rings are either wide or narrow, or wide or narrow. And so they're developing a barcode going back in time that's unique in time.
Using this pattern, David was able to work out exactly when the trees had died. And he found out that all of them had died around the early months of 1700.
The summer before the tsunami hit Japan, these trees were just growing happily in the forest here. Then the winter came along, and by the following summer, they were all dead. And so the tree ring story matched the Japanese tsunami records perfectly.
There was now no doubt that the same catastrophe that had killed the Ghost Forest had also sent the tsunami across to Japan. And from the Japanese records, Kenji Satake could work out exactly when it had happened. On the 26th of January, 1700, at 9 p.m. On that winter's night, a megathrust earthquake, just like the Boxing Day earthquake of 2004, struck the Pacific Northwest. It drowned forests and turned land into sea. It sent a tsunami hurtling across the Pacific, and it spawned a legend that would be passed down through a dozen generations. The scientists knew that if it had happened here once, it would happen again. One day, the people of the Pacific Northwest will face a megathrust earthquake. So how big will it be? What damage will it cause? And when will it happen? The first question is, how large will the earthquake be? The power of an earthquake depends on the size of the fault that breaks. In the case of the Boxing Day earthquake, it was huge. Over 600 miles of fault ruptured. The Cascadia subduction zone is almost exactly the same length, so it's likely that it will create an equally powerful earthquake.
Now, we do not know exactly when the next Cascadia earthquake is going to occur, but we do know that the impact of that earthquake in terms of the ground shaking, the huge area impacted, the extent of land level changes, the size of the tsunami which will be generated will be very comparable to that which was seen on December the 26th in 2004.
Scientists believe the next Cascadia earthquake will be one of the largest on the planet, up to magnitude 9. The Kobe earthquake, which killed 6,000 people and devastated the Japanese economy, was a magnitude 6.8. The terrible Mexico City earthquake, which killed over 10,000 people, was 8.1. But a magnitude 9 releases many times more energy than those.
The magnitude scale is logarithmic, that is, each one is 10 times bigger than the previous number, but that's the amount of displacement. When you do that in terms of energy release, each one is 30 to 40 times bigger than the previous one. So a magnitude 9 has 1,000 times more energy release than does a magnitude 7, 30,000 more than a magnitude 6. So to put that in perspective, the Kobe earthquake that was so damaging in Japan was about a magnitude 6.8. So a Cascadia event that would reach magnitude 9 is more than 1,000 times bigger than that one.
Just as happened in the Indian Ocean, this huge earthquake will cause a sudden uplift of the sea floor, and that will create a tsunami. The Boxing Day tsunami devastated the densely populated northwest coast of Sumatra and almost totally destroyed the town of Banda Aceh. The cities of Seattle, Portland and Vancouver will at least be spared that fate.
One of the fortunate things about Cascadia in comparison with northern Sumatra is that the big towns and cities aren't located right out on the open ocean coast. The complex of waterways in Washington state means that the big ports are actually located some way inland.
However, thousands of people do live on the Pacific Northwest coast, and in summer, the beaches are a major draw to tourists.
A lot of the population on the Washington coast is vacationers. The population can grow from just a few thousand permanent population to tens of thousands of visitors. And if we have a Cascadia subduction zone earthquake and tsunami, the wave crest would arrive at places like Ocean Shores and Long Beach within about a half hour. And that's a very short period of time to be able to move a lot of people off those peninsulas to high ground.
So even though there are no major cities on the coast, there will still be many thousands of people at risk from the tsunami. But far more people will be affected by the earthquake itself. All the major cities in Washington, Oregon, and British Columbia are going to experience strong ground shaking. And this megathrust earthquake will be very different from a normal quake.
Magnitude 9 earthquakes have these special characteristics. One of them is that it takes several minutes for the fault to break from one end to the other. The fault rupture spreads out at a few kilometers a second, but it still may take 2 or 3 minutes to get from one end to the other. And that means the earthquake shaking goes on for a very long period of time.
If the full 600-mile length of the Cascadia subduction zone ruptures, it will mean the earthquake will continue for as long as 5 minutes, just like the Indonesian earthquake did.
The duration of the event is very unusual, and in that sense alone, it can cause more damage. A quake that goes on for longer causes more damage generally than one that is over within 10 or 20 seconds.
So what damage will several minutes of shaking do to cities like Seattle? Even though the Boxing Day earthquake and the next Cascadia earthquake may be very similar, they could have very different effects. In Indonesia, most of the damage was caused by the tsunami, not the earthquake itself.
Most people's houses are built out of wood. There's some more modern concrete construction, but typically only 1 or 2 story buildings. So that these buildings are not sensitive to the very long period ground motions we can expect from a magnitude 9 earthquake.
But the modern high-rise structures of the Pacific Northwest may react very differently. Tom Heaton is an earthquake engineer from California. He was brought in to advise on the construction of a nuclear power station near the Washington coast. In the end, the project ran out of money and was never completed. But ever since, Heaton has been concerned by the question of what damage a Cascadia earthquake could do, particularly to skyscrapers.
My fear is that in a Cascadia event, these buildings may sway some large distance, and as we get a very long duration of shaking, that the swaying may grow in intensity, and the buildings may begin to be damaged.
But not everyone agrees. John Hooper is a buildings engineer who has worked on many of Seattle's tallest buildings. He believes that the modern skyscrapers, at least, should be strong enough to avoid serious damage.
Majority of the high-rises here, they'll move, and they'll move a lot, but they're designed to withstand that motion and that energy absorption, and they go through that 8 or 10-foot drift back and forth during the earthquake for several minutes, scaring a lot of people probably, but the damage should be related mainly to the non-structural components and not to the major structural elements themselves.
The reality is, no one knows for sure, because there has never been a megathrust earthquake near a modern high-rise city.
These very large earthquakes don't happen often enough for us to understand what it is we need to do in the first place. So the building codes have never really been tested by an earthquake of this nature, at least not for tall buildings. The lessons haven't been learned yet. So what concerns me is that we may learn the lesson in a very difficult way.
But there is a type of building that everyone agrees will be at risk. The older brick buildings, known as unreinforced masonry, or URMs.
These buildings we see around here in Pioneer Square, like many cities on the West Coast, they're constructed of unreinforced masonry, bricks stacked upon bricks separated by mortar. And so if an earthquake shaking happens, those bricks end up sliding past one another and they lift apart.
URM buildings are very weak and very brittle. So the long duration of shaking that a megathrust earthquake will produce could cause many to collapse.
URM buildings have been noticeably not very resistant to earthquakes in general. And if you don't do some renovations and start connecting the pieces together, they're very susceptible to damage, especially in a long event like the Cascadia. And so even those that do have some improvements made to them, they still might be challenged. But those that don't have any, their chance of surviving is probably fairly limited.
There are thousands of these unreinforced masonry buildings in the earthquake zone. They are used as homes, offices, and schools. The collapse of such buildings is likely to be a major cause of death and injury when the next Cascadia earthquake occurs. So the big question is, when will it happen? Predicting earthquakes is impossible. No one could have known that the Indonesian earthquake was about to happen. And no one can say when Cascadia will strike. But it is possible to look back at the geological record and see how frequently earthquakes occur on a particular fault. Sure enough, the Washington coast does hold traces of several past megathrust earthquakes, from even before 1700.
About 2,500 years of earthquake history. 1, 2, 3, 4 events recorded. Radiocarbon ages show that this event happened about 600 years BC, and that this event happened about AD 400. So something about 1,000 years between this event and this event, a very, very long time. This event's from about AD 700. There are only about 3 centuries between this event and this event. This is about the same amount of time as between here and today. So this is why it would not be surprising if, while we're standing here, another one of these great Cascadia earthquakes happened and we have to run to high ground.
And that is the problem. The next megathrust earthquake may not happen for centuries. Or it could be imminent. No one knows. We don't know whether the entire Cascadia fault will rupture like it did in 1700. We don't know how badly affected the modern cities will be. But Yumei Wang, Director of Geohazards for Oregon, believes we must still take action.
We know that a Cascadia earthquake is inevitable. We can't prevent earthquakes, but one thing that we can do is prevent a lot of the damage. We can save lives if we prepare now.
That preparation must be based on our current understanding of what the next Cascadia earthquake will be like. What follows is a reconstruction based on the knowledge of leading experts of what may happen, what it would look and feel like to experience a megathrust earthquake.
We don't know what actually sets the earthquake off, but typically it would probably start at some rough spot on the fault.
The rupture is most likely to start at one end of the fault. It would then spread along the fault at over 7,000 miles per hour. As it tears, the North American plate, which has been pushed inwards, would spring back, releasing the strain.
There may be a region 400 or 500 kilometers long where the seafloor has suddenly risen up by 2 or 3 meters. It happens so fast that it lifts up the whole body of the water on top of it. And as a result, suddenly the sea surface finds itself 2 or 3 meters higher than it was before, over a large area, and that sets off a wave.
This is the tsunami, which would radiate out in all directions. Part of it would head out into the Pacific, and part would head directly for the coast of North America.
It travels at the same speed, roughly, as an airliner out in the open ocean, perhaps 600 miles an hour.
Even at that speed, it would take many hours to reach the other Pacific nations. It would take 5 hours to reach Hawaii, and more than 10 hours to reach Japan. Thanks to the sophisticated Pacific Tsunami Network, those countries would get a warning.
The quake will be detected by a network of seismographs. The tsunami, if they form, will be spotted and identified and tracked by seabed sensors, which will send via buoys on the surface a radio message via satellite to the emergency authorities in the countries around the Pacific Rim who might be affected. It's then their job to tell their populations to evacuate the coastal region.
This warning system should make the distant effects of a Cascadia earthquake very different from the events of Boxing Day.
I think that the loss of life remote from the actual location of the Cascadia earthquake will be small when the next big event occurs. And this is because although the waves travel at the speed of a jumbo jet, maybe 800 or 900 kilometers an hour across the Pacific, it's a huge ocean basin, and it will take many hours for the waves to reach places like Hawaii and Japan, which will probably be badly hit, but they will have plenty of time to evacuate people to safe ground.
But the situation in the Pacific Northwest would be very different. The tsunami would arrive there in half an hour, and they'd have the earthquake to deal with first. The seismic waves which carry the shaking would be traveling through the Earth at over 10,000 miles per hour, much faster than the tsunami. In just a few seconds, the earthquake would reach the land. The earthquake would be at its most violent here on the coast.
They're right at ground zero of the shaking, so the shaking they feel will be the largest of anybody because they're nearest to the fault rupture.
But the shaking wouldn't have reached the inland cities yet. People here wouldn't even know that an earthquake had started. However, news would have reached the emergency services. This is the Washington State Emergency Operations Center. It would be one of the first places to receive an alert from the Tsunami Warning Center.
Preliminary magnitude 9. We're activating our EOC to a phase 3 for a tsunami.
Horizon filmed them rehearsing for a major earthquake. The two on-duty officers would immediately activate the center and start calling in staff.
And what could be your possible ETA to the EOC?
Okay. Their job would be to coordinate the emergency response. But there would be no time to issue a public warning before the earthquake hits the big cities. Up to 2 minutes after the start of the earthquake, the seismic waves would reach the city of Seattle. Because of the distance, the different types of seismic wave would have separated out, with the faster compression waves reaching the city first.
The first thing you sense is a vertical acceleration. You get pushed up a little bit, and you think it's maybe a jolt of a train going by or something of that type.
But then later, maybe 20 seconds even later, you might start to feel the shear waves coming in, which are shearing motions in the earth, the kind of motion that does most of the damage.
These shear waves would move the earth from side to side by as much as a meter. There would also be surface waves, like ocean waves rippling through the solid earth.
If you are in a parking lot, it's likely that you see waves rolling across the parking lot, like if you took a carpet and shook it.
As the shaking becomes more and more intense, people would realize that this was no ordinary earthquake.
That shaking will continue to build. You'll feel the first sway, and it'll start to build and build and build, and you'll wonder when it's going to stop.
Indoors, objects and furniture would be hurled around the room. Parts of the building may start to fall.
Right when you feel the earthquake shaking, what we train people to do is to duck, cover, and hold.
Schools and offices now practice this life-saving maneuver, going under a strong desk and holding onto it.
Anything that might fall won't fall on you directly, it will fall on the table, and the whole time you protect your...
For people outside, the major hazard would be falling debris and shattering glass.
If you're outside somewhere, the best thing to do is to move quickly into open space, such as away from a building where you might have falling objects.
Buildings would now be exposed to huge forces as they're shunted back and forth. The unreinforced masonry buildings would be the first to suffer damage.
The weakest points start to fail. In most cases, because they're older structures, it's the mortar.
The elements that support the building vertically, if they start to come down, the floors themselves potentially can come down.
Collapsing URMs could cause many fatalities throughout the region. The shaking in Seattle would now have been going on for 2 minutes, but we'd only be halfway through.
For a typical earthquake, if a building gets damaged in the first 20-30 seconds, it very likely can remain standing. But if that damaged building is shaken for another 3 minutes, then that damage can propagate into collapse.
Meanwhile, the large movements of the ground would be making skyscrapers bend further and further.
You may see the buildings begin to sway more and more violently to the point where they start to perhaps lose windows. They may, in addition, start to have some fracturing of welds in steel frame buildings. What happens after that is anybody's guess.
The worst case scenario would be the total collapse of a high-rise building. Meanwhile, buildings on higher ground would be suffering their own problems.
Earthquakes this large can generate landslides at distances up to hundreds of miles away.
The classic worst case scenario where you're on a hill, a landslide, your house goes with it, and the house will obviously be destroyed.
Five minutes after the start of the earthquake, the rupture would have reached the northern end of the fault. Vancouver would still be experiencing powerful shaking. But in Seattle, the earthquake would finally be subsiding. For people in buildings that have suffered structural damage, now it would be time to evacuate. What would have felt like the longest few minutes of people's lives will finally be over. But on the coast, the ordeal would have only just begun. The tsunami, unleashed by the earthquake, would be minutes away. For the Pacific Northwest, the tsunami warning system that should save lives across the world would be virtually useless.
There won't be time for the Tsunami Warning Center to detect that earthquake, make a determination whether or not it was tsunamigenic, then send a warning down to emergency managers in Washington, who will then send it to the people. That would waste valuable time. People need to know that when they feel strong shaking, if they're on the coast, they need to go to high ground and or inland.
The tsunami will have started out as a wave of only 1 meter or 2 high, traveling at huge speed. But as it nears the coast, it starts to rise up.
Those waves can grow, they can amplify as more and more water piles up in shallow water, and all of that energy then causes the wave to slow down and grow in amplitude and create waves that have been known to be hundreds of feet high.
That first wave is often simply a step in the water level, and the water level then stays up high for 5 or 10 minutes before it eventually drains away again.
Just as happened in Indonesia, within half an hour of the earthquake, the tsunami would rush onto the land, more like an ever-growing tide than a normal wave. Anyone who doesn't manage to get inland or to high ground in time would be unlikely to survive. The tsunami will devastate hundreds of miles of coast. In total, more than 50,000 square miles will be affected by the earthquake.
Unfortunately, I don't think people understand that a Cascadia earthquake is going to be so very different than the other types of earthquakes that we've all experienced, or many of us have experienced. One of the main differences is that it's going to affect such a large region.
It's not just going to be city of Seattle or city of Portland. It could be an 800-mile stretch of Washington, Oregon, and California that gets affected.
Until recently, many people would have found it difficult to imagine that scale of devastation. But the Boxing Day disaster changed all that.
The Indian Ocean earthquake and tsunami will remind those people that are living in the Pacific Northwest that this is something they will have to face in the future. And the window of opportunity that now exists should be used to make sure that the people that live in that part of the world are educated in terms of how to respond when the earthquake happens.
Quickly, all of you.
The simple knowledge that after an earthquake, people should move away from the ocean and to high ground can save lives. The scientists who discovered this threat are now playing their part in spreading the word to as many people as possible.
It goes all the way up to a salt marsh. So I start here.
Before the next earthquake.
We know that this Cascadia earthquake is imminent. It's imminent in geologic time. So basically, we're in a race against time. And the more we can get done now, the more lives we'll save.
If we have 10 years, is that enough? Probably not. If we have 50 years, maybe. If we have a century, maybe we'll really be ready. But do we have a century? We don't know.
The Indonesian earthquake has given the people of the Pacific Northwest a glimpse of what they will one day face. Now, they must heed that warning.